No. So yes, today it's my great pleasure to welcome Anna Klimovic here with us. She's an assistant professor at ETH Zurich, which is one of the worldwide leading institutions when it comes to computer science and many other areas. So she has been with Google Brain before going to ETH. Before that, I believe a PhD at Stanford. And she is working on a connection of topics that include hardware topics, operating systems, and in particular interactions with machine learning. That is what her talk today is going to center on. She's going to talk about scalable machine learning by in particular making the input data processing scalable, because as you can imagine, if we don't provide those systems with a steady stream of data, then we are slowing things down. And she's going to discuss in particular a system called Cachew, which increases efficiency in that space very efficiently. So without further ado, please tell us more about that.
Great, thank you very much for the intro. Happy to be here. So I couldn't be there in person, but glad we can make it work for the seminar. So yeah, it's an exciting time to be building systems for ML because there's huge growth in this space, right? There's lots of new ML use cases. The sizes of models are growing. The sizes of the data sets that we need to train these models are also growing, and the amount of data that we can collect has been growing. So these all present interesting system challenges. And at the same time, there's been growth in the kind of compute capabilities of the hardware. So just giving Google's TPU pod as an example here, but really this huge progress in machine learning has been largely enabled by this kind of hardware acceleration that we can use to make these computations higher performance, higher throughput, and more energy efficient. But along with this exciting growth, there's been a growth in cost. And this is kind of one of the main challenges today, is that we can train models that have high accuracy and are useful in all kinds of tasks, but it does consume many GPU or TPU hours and many dollars to actually achieve this. So as a fun kind of intro to this, this is an example from one of my favorite colleagues, Zhang, who had a project collaboration with some folks in industry as well. And they were training a recommendation style model, which has many, many parameters. It they trained it for 1 day on the cloud. And I'll give you a hint as to kind of what resources they used. And then I'm curious, how much do you think this cost? So they used 3,000 CPU cores, 64 A100 GPUs, and 360 terabytes of RAM for 1 day on, I think it was Google Cloud that they were using. So I don't know if I can actually see the room, but maybe you can tell me who thinks it's 4,000.
It's the votes.
Okay.
Count the votes for you.
Okay, okay. Any votes for 4,000 or no?
Nobody.
Okay. What about 40,000?
Two persons, right?
Okay. And 400,000?
Most of us. 4 votes.
Okay. Okay. Cool. So you're getting the point that this is expensive. This was still, done on the academic side. So it was 40,000 in this case. And they have actually a blog article where they elaborate on sort of the optimizations they did, or kind of their setup here for this project. But even this, 40,000 in 1 day is kind of, burning one of these nice Mercedes vehicles in 1 day is also, a lot. And so, yeah, and one kind of big challenge is kind of how do we address this cost and resource efficiency problem of ML? Just another example, celebrating that we can train a GPT-3 quality model for just under 500,000. I mean, it's exciting, but yeah, it's still 500,000. So we need to think about how to make these types of things more scalable. And so kind of the overarching question here is going to be, how can we reduce the cost of ML? We're going to look particularly at training, although, of course, inference is also a huge part of this. You train the model once, or maybe you train it multiple times to update it. We'll get to that aspect a bit later in the talk, but then you serve it a lot. So in the context of this talk, of course, we have to sort of contain a little bit or decide what to focus on. So we'll mostly be talking about training. But even if we're just focusing on ML training, there's all kinds of ways you can think of approaching this question of how to reduce cost. And I think the most exciting approaches are sort of really at this intersection of systems and ML. So you can look at, looking at the resources, the actual hardware you're using, and saying, how can we make sure that whatever hardware nodes we allocated to this job, that they're being utilized as effectively as possible, so that we need the minimal amount of hardware to get to the final result. So that's what I'll talk about in terms of resource efficiency. And I'll just briefly, kind of at a high level, describe what I mean by data efficiency. So here, the cost of training a model is proportional to how much data you actually visit to train that model. And of course, we're collecting a lot of data, but that makes it, and that's important to train to high accuracy, but not all data is equal. Some examples are more important than others, and being able to actually detect this and have system infrastructure that's built with a notion of data importance in mind can actually help reduce the cost. And model efficiency, I won't go into this talk, but an example of this would be something like the pathways networks or something with sparsely activated model architectures, where to train on a particular piece of data, you don't actually need to invoke the entire model, but rather you can route an example through a subset of the model and share knowledge from different examples, but activate the model in a sparse way to make it more energy and cost efficient. Okay, so all kinds of different approaches that we could take, and I think it's really necessary to look at all these types of dimensions in parallel to really address this cost and resource efficiency problem. Okay, so in this talk, I'm mostly going to focus on resource efficiency, and I'll touch a little bit about how we're starting to think about data efficiency, particularly in this context of updating models and new data streaming in and how to incorporate it towards the end of the talk. Okay, and please feel free to interrupt at any point. Happy to take questions along the way. But please speak up, because I can't actually see everyone in the room. So just speak up if you have a question. All right, so what I mean by resource efficiency is ensuring that whatever hardware we've given to our ML job, that it's well utilized. Okay, so you might ask, well, why wouldn't it be well utilized? ML training is compute and memory intensive. These GPUs, probably should be highly utilized. But there's many things that could be bottlenecking your ML job. Some of it can be communication between distributed nodes or various kinds of things. But one big one, which we'll focus on quite a bit in this talk, is all the stuff you need to do to your data before you feed it to something like a GPU or TPU for training. All right, so you have your raw data, and before you feed it to your model, you need to do some sort of preprocessing, okay? And I want to distinguish between two types of preprocessing in particular. Some of these kind of things, like extracting the features, cleaning the data, normalizing, a lot of this you can do offline. So common frameworks you might use are Spark or Flume, Beam, etc. And these typically have a global view of the whole data set that's needed actually to do these kind of operations like normalization. And then you materialize the outputs of that preprocessing step, okay? But you're not usually quite done with the preprocessing. Usually while you're actually training, you're reading this output of the offline preprocessing. And then on the fly, as you're training, you're reading some elements from the storage, and you are actually often applying some other, what I'll call online preprocessing operations, or sometimes also called last mile data processing. And this is typically to apply things that you want to tune to the particular job. So maybe the batch size depends on what kind of GPU you're using and how much memory it has, etc. But also things that maybe augment the size of the data and make it actually more practical to do on the fly versus materialize, or where it's not super clear. Like, for example, in image processing, you maybe want to teach the model this is a cat, regardless of if it's in the bottom left or the top right of the image. And so every time you visit this particular cat image, you may permute it in a different way to make your model train to a higher accuracy and to be more robust. And this is an example of a common online preprocessing operation. Or you might filter some features while you're experimenting, which features are actually going to be most important. You might subsample the actual elements, etc. So these are all examples of things that you're doing to the data on the fly as you're training. And this is particularly important to optimize because it's on the critical path of the actual training batch, right? So it impacts the training time and it really impacts the cost. Because the really expensive thing here is especially this hardware, the GPU or TPU. But what can happen is because data processing is typically happening on the CPU because it needs to support generic user-defined types of operators, if this part of the pipeline is your bottleneck, then you end up stalling the GPU and idling it, which becomes very expensive. Okay, and this gap is widening, of course, between the CPU performance and GPU. So it's something we especially need to be mindful of. And not only do you want to make sure that step of the pipeline is not a bottleneck, but actually the input data processing itself consumes a non-negligible amount of CPU power and energy. So there's different ways that you can study this, and this is kind of one of the interesting things that you can do in industry where you have a whole fleet of jobs and you can instrument them. So at Google, we did this. We instrumented the fleet of ML workloads over a 1-month period, and these are TensorFlow jobs, and we can actually look at what fraction of the time in those machine learning jobs was spent inside of the data processing library. Okay, so this is called tf.data in TensorFlow, and we found that on average about 30% of compute time was spent for data processing out of like all the things that the job is doing, including the actual training itself. And at Meta, they did another study where they focused especially on recommender system models, and they found that actually for some cases, data processing and fetching the data, preprocessing it, consumed more power than the training itself. Okay, so we talk about training being very expensive computationally, but input data processing is also a non-trivial amount. Depends on the job, of course, but this is a part of the pipeline that we need to pay attention to. Okay. Any questions so far about the motivation? Okay, I guess we're all data people. Okay. Okay, so then the question is, what can we do to ensure that that part of the pipeline is not a bottleneck? Okay, so I'll talk about kind of two main strategies, which kind of go towards this Cachew system that we built, but I'll introduce them gradually and how we built on top of the TensorFlow framework called tf.data. So one aspect that I'll talk about is, if first of all, you need to detect that you have an input data bottleneck, okay, that is what is slowing down your pipeline. And then there's various strategies you could do. NVIDIA's strategy, I mean, for example, they have something that allows you to offload things to the GPU. That's an option. The part what we chose to do to make it, support any kind of user-defined computation that you would already do today is, well, if you're bottlenecked on how much CPU and RAM you have on this particular machine, then how about disaggregate and distribute your data processing across remote CPU nodes? Okay, so because each job will have a different balance of how much preprocessing it needs to do for each training step, and your hardware comes in these sort of fixed configurations, to make things more flexible, you can disaggregate and scale up and down the GPUs separately from how many CPUs you're using for the preprocessing. And you can do this by enabling preprocessing to be done in a remote or distributed fashion. So we'll talk about how we do that. And then the other nice thing is once you decouple data processing, you can build a service that has a global view of what is all the data preprocessing that all of my ML jobs in an organization are doing. And this is something that you didn't have before because each job was kind of doing its own data processing without awareness of, am I reading the same data that a bunch of other jobs are reading? And are we all pre-processing this in a very similar way, potentially? And because of a lot of machine learning workflows like hyperparameter tuning and things like this, it's actually quite common to have quite a bit of overlap. And if you have a disaggregated data processing service, then this can have a global view of data processing across jobs and detect these kind of opportunities to deduplicate and cache. So these are two kind of key ideas that I'll show you how we incorporate into a service that automates these things for users. Right, because the people who are actually using this are ML practitioners who are not necessarily systems experts and don't want to be the ones configuring exactly how many nodes to use, etc. So the idea is to automate things. But before we kind of dive into how we implement those key ideas, I'll just give a bit of background on the framework that we're actually going to be using and extending for this. So tf.data is the data loading library in TensorFlow. I'm not sure, maybe some of you are already quite familiar with it. Maybe not, but the API is similar to things that you might have in Spark, etc. The idea is you have generic operators that can be composed and they can also be parameterized. So you have, let's say, a read operator and you pass in a file, you have a map, or you have some user-defined function, you can have a filter, etc. And you basically chain these different operators, and then you can iterate to actually get data through this pipeline. Now, and this API is in Python. This is, and we'll see an example in a bit to make it more concrete. But this is kind of an easy-to-use API for users. Under the hood, what happens is the C++ runtime is in charge of actually efficiently executing these input pipelines. So it's going to apply all kinds of optimizations like software pipelining, parallelism, fusing operators, and auto-tuning parameters like what's the prefetch buffer size, or how much parallelism, how many threads should we use in this map function, and things like this. And so just to kind of give you an idea of what it looks like to build a tf.data pipeline using the API. So you would have this dataset object that you initialize first with the source data. So in this example, we're reading a TF record dataset that is stored at this location. And then we sort of just chain these different operators on top, right? So we're going to apply a preprocessed user-defined function on the map as the input to the map. Then we're going to batch the data to make it more efficient to do this on GPUs afterwards. And we can also prefetch a certain number of elements to help with software pipelining. And then we just feed this dataset object directly where we're doing our actual model training here. Now, I mentioned tf.data applies different kinds of optimizations under the hood. So it does things like it can parallelize the reads, it can parallelize the map operations that you're doing, and it can sort of adjust this prefetch buffer size. And as a user, you can, if you want, clearly tune and specify these values yourself, or you can specify like a tf.data auto-tune constant, or parameter, which will trigger the tf.data runtime to dynamically try out different values and optimize this under the hood. So I won't go into the details of its algorithm. This is also something we explored in a project called Plumber, which was about kind of finding the bottlenecks and adjusting parameters to try to smooth out these bottlenecks and make sure that the throughput is quite constant throughout your pipeline. The way the algorithm works in the kind of default tf.data system that you can fork from TensorFlow now is it's a hill climbing algorithm that's treating each of these operators as a queue and predicting what is the expected output latency as we adjust these different parameters, and then picking these parameters to minimize that output latency or otherwise optimize the throughput.
One question.
Mm-hmm.
Would these techniques extend if I have a custom function to pre-process the data that does not use like well-defined functions like map or batch? Suppose I write my own preprocessor.
Right. So, okay. So the only thing that to be able to use map, so preprocess would be like your own user-defined function. The only thing is it should be something that applies this operation per element. So this is kind of it's a bit of the streaming programming model style. tf.data is not designed for things where you, let's say, need to join, or you need to have a whole visibility of the entire data set to do a particular operation. It's meant for this sort of on the fly, I get data, I need to do some transformation to it. Does that answer your question?
Yeah.
Okay. Okay, so in the interest of time, I won't dive too deep into the auto tuning. Happy to chat about it if people have questions, but I was.
Another question.
Yeah, okay.
Isn't TensorFlow being like not deprecated but losing like official support? Are you guys worried about that at all?
Losing official support. I haven't heard about that actually. I'm aware that PyTorch is increasingly, kind of being used, especially for these kind of newer models, etc. I guess at Google, my understanding is that it's still quite widely used. And the other thing is that tf.data is not, it's built to really interoperate and be, it's part of TensorFlow. But you can actually, and especially when we talk about disaggregating, you can still use tf.data to have this programming model and to have this input pipeline and the optimizations under the hood. But you could plug in actually a PyTorch model or some other framework model to do the training part. So you're not here the way I've shown it. We haven't yet done the disaggregation, but I'll show you that's just a small addition to the API, like a one-line thing that you say distribute, and you could use the tf.data framework even if you're not relying on TensorFlow for your actual model training part. About the losing support and stuff, I'm not the best person to ask. I guess I should catch up on that actually, if that's the case. Yeah. All right. Any other questions before we move on? Okay, cool. So auto-tuning, these kind of parameters, like how much parallelism should I have in these different operators, what's the prefetch buffer size? This is all useful, but basically the best we can do is, we fully utilize whatever CPU and memory resources we have on this node, and we use them to the best, we share the CPU cores and the memory optimally across the different operators in this pipeline to maximize throughput. But it could still happen that we just don't have, it's still a bottleneck compared to the step time of the actual training, simply because we don't have enough hardware resources. We don't have enough CPU cycle cores and memory here, okay? And so this question of, how should you provision the CPU and RAM resources per GPU and TPU is a hard one to answer because there is no right answer for everything, right? Depending on your job, you're going to have different needs. So here's just an example with 3 different ML models. And what we're varying on the x-axis here is how many CPU cores we have per accelerator core. Okay, and on the y-axis, we're plotting the epoch time, so the time it takes to train over a full iteration of the data set. And this eventually flattens out because at some point, here, when you don't have enough CPU cores, you're input bound. And so you have very high epoch time because of that input bottleneck. And as you give it more CPU cores, that input bottleneck goes away. But the point at which it's optimal to do this is going to depend on the particular model. And we actually, to kind of understand how wide is this distribution across, let's say, the Google fleet. This was another kind of part of the analysis that we did. We looked at, okay, this graph is maybe not super intuitive to understand right away. So let me explain what's the best way to read this. So we looked at 73,000 machine learning jobs in the Google fleet. And we sort of had to normalize the values here. So we're not showing the actual number of CPU cores or RAM, but we're showing it as a distribution. Okay, so the 100% here, this is the job that out of these 73,000 needed the most CPU for its preprocessing, and likewise the most memory here. Okay, and the goal here is not really to talk about the concrete actual number of CPU cores in RAM, but rather this distribution, which has a relatively long tail, right? And if you pick a certain ratio of compute and of CPU and memory to your GPU, you're basically picking, one sliver here. You're picking for one job, it's going to be ideal, or for, a small set of jobs, it's going to be the right ratio. But for a large chunk of jobs, you're going to have over-provisioned CPU, and those resources are sitting idle. And for many jobs, you would have been actually not having enough CPU, which causes the input bottleneck and causes the expensive GPUs and TPUs to idle. So that's even more problematic. And so the point, this is all kind of motivating, actually, that it's really hard to get one great configuration that's going to work for all the jobs, and the job requirements change over time. And this is, the standard thing that comes up when trying to do resource allocation, whether it's because you have TPUs and CPUs, or storage and compute, etc. Let's see if this turns on. And a common solution is then to disaggregate and say, well, let's try and scale these resources independently. Okay, and so the idea is, this CPU core on this local machine where the GPU is great, and we want to use it, but we also want to use the remote CPUs that are available around and have some spare capacity and memory, and also CPU cycles. And if we can, recruit the optimal number of these remote nodes to remove the input bottleneck in this job, that's what our goal is, really. And finding that sweet spot, you don't want to distribute too much, because these remote nodes also have a cost, right?
I have a question.
Yes. Mm-hmm.
In the previous slide,
Mm-hmm.
the figure on the left-hand side, does it show that like more than 80% of the jobs, only 20% is that the CPU uses, meaning that like 80% of the CPU is not all bottleneck, but something else is.
You're asking, does it show that for 80% of jobs?
Yes, so CPU uses is around 20%.
Yeah, okay, so this is not, no, that's not what it's showing. Yeah, thanks for asking. So it's not utilization. This is not, it's really usage, and it's normalized. So this says nothing about which hardware this is actually scheduled on. It doesn't say what's the utilization of the CPU and the memory on the hardware. It just says, basically how many CPU cycles were needed, and how much, gigabytes of RAM were consumed. So it's not about, because what we were trying to show here is not, in the current config, what's the utilization that you would get, but it's really, what is the demand, and what's the distribution of the demand, to show that there's no right, one or two configurations that's just going to satisfy everything here. Does that make sense?
Thank you.
Okay. Yeah, good questions. Any other questions? Okay. So I was saying this leads us to this kind of natural solution of disaggregation, similar idea to how, disaggregating storage or memory from compute can have similar advantages of giving you more flexible ways to allocate resources and adjust to the unique demands of separate applications. Okay. And Google's not the only one taking this approach, and this is work that we've been doing in collaboration with Google. Actually, this paper just recently got accepted. It'll be appearing at SOCC in a month. But Meta also has a paper, I think this is an ISCA paper, on their system called DPP, so data preprocessing system that they have. And actually, they're motivating, this is the paper also that showed that data processing can consume more power than training itself. And that also led them to consider a disaggregated and use a disaggregated architecture. Their architecture, as far as I know, last time I checked, it was not open source. It builds on top of PyTorch, and they describe some of their mechanisms in the paper. What I'll do is I'll continue discussing things in the context of tf.data service, but these ideas of disaggregating are applicable to other frameworks as well. So in the kind of conventional, before we disaggregated, we had this training job. It runs on a particular training client that has the actual GPU, TPU, or multiple of them. And this is initially where you would also be doing your data processing. Now what we're saying with tf.data service, we disaggregate this by saying this client is actually going to register its input data pipeline to the dispatcher. Okay, so that's sort of the brain of the tf.data service, which is keeping track of what are all the input data pipelines that this service is responsible for. And the dispatcher is going to recruit data workers. So these are CPU workers. It is going to have, we'll see soon, we're going to add this function. Like the baseline tf.data service is the user decides how many workers to instantiate their service for. Eventually, what we'll get to in the design is that we're going to be auto-tuning that decision, because that's actually a non-trivial thing for users to decide. And what happens is the dispatcher notifies the client, these are the IP addresses of the workers that you should fetch data from. And so what the client gets from these workers is actually data that's ready to feed into the GPU or TPU for training. Okay, now what actually gets sent over? How does the, I mentioned tf.data is kind of has this API of operators and kind of represented as a DAG of operators that are chained together. And so that DAG is actually the representation of the input pipeline, and this is what gets sent to the dispatcher. It represents here the actual operations that need to get executed, and the dispatcher will send that pipeline representation to all the workers that are involved in this job. And then it'll also tell the workers, here's the slice of input data that you're going to use, that you're going to apply that pipeline on. So the workers can work in parallel, but they're working on different parts of the data set, and they're feeding the results of the preprocessing to the client. Okay, any questions with how the service works? Okay, cool. How does this actually look from the user perspective? This is a very similar pipeline to what we saw before. To make this disaggregated, the user would just have to add this one line to say, take this data set and now distribute it, and specify the IP address of the dispatcher, right? So this line is what's really registering that input pipeline with the dispatcher. But from here on, kind of all the clients fetching things from workers under the hood, this is all abstracted from the user. Okay, so what does this actually mean for performance, right? The main benefit of disaggregation is that we can respond and kind of eliminate or heavily alleviate input bottlenecks. And this can have a huge impact in performance. Of course, it really depends what your workload was, how input bound it was before you decided to disaggregate. And here what I'm showing, this is from a analysis that we did at Google. This is with Dan Grauer, who I co-advise at ETH. And during his internship at Google, he looked at various models in production. These are vision models that we don't really get to share the complete architecture details of, but basically things like object recognition and things like that. And the baseline here on this log plot on the y-axis is the co-located. So on whatever hardware is by default, the CPU and memory available by default on TPU machines. If you were limited to using the associated CPU and memory on those nodes, that's the performance that you would get. And then ideal is, if we just kind of have a fake input pipeline that's feeding garbage data, but at a really fast pace, so the GPU or TPU always has something to train on. This is just a throughput test. That's the green line. So that's kind of where we're definitely model bound, no longer input bound. So there's a huge opportunity for speed up. And the orange here is showing that we can close that gap with this disaggregated approach. So by recruiting extra CPU workers, we get to remove that input bottleneck and feed data fast enough to satisfy the training ingestion. And you can see that in some cases, like the speed ups are even 2 orders of magnitude. So it kind of makes sense that we can improve performance, that we can find these input bottlenecks and alleviate them. I guess the bigger question is what happens to cost, right? Because we're using more resources to do this. Okay, but it turns out that cost actually is reduced as well, quite significantly, not quite as significantly as the performance. But what's really happening here is this performance delta, this improvement, this speed up is so significant that, and the cost of the TPU or the GPU is the most dominant part of the hardware that you're using in ML jobs. And so the fact that you can finish the job faster and release those TPUs or GPUs faster is what actually contributes to this major cost reduction that you can still achieve. So this is for the same 3 models and the same experiments. This is if we take into account the extra CPU and memory that we used for the data workers, the overall cost that we achieve is still a lot lower because the job just runs much faster. Okay, so this is sort of arguing that putting those extra resources in is worth it. Okay, and this is in cases where your job was heavily input bound. You do need to be able to detect this, and you need to be able to find this sort of sweet spot of using the right number of workers. And that's what we'll get to in a bit. But any questions on this so far? Okay.
Oh, there's one question.
Yeah,
Yes.
is there a particular reason why the M2 model had the biggest improvements, or is that just like the nature of
Okay, so why does the M2 model? Yeah, so basically the relationship, it means that the relation of how much preprocessing compute intensity or memory intensity it has versus the compute intensity of the training batch is most balanced towards it has to do a lot of preprocessing for every training step. And so this is the model that also needed to spread to more and more compute nodes to eliminate that input bottleneck. But overall, this ends up being worth it.
Thank you.
Sure. Okay. Okay, so we talked about this disaggregated service, and I said, actually, another nice thing you can do. Okay, never mind. So maybe I'll talk about auto-scaling first, and then we'll talk about caching. So the thing is, it's nice that we can pick now flexibly the number of workers, but actually picking that number is not easy for users or ML practitioners to do. So ideally, we would like to automate this. And the other nice thing is that we can actually use this service not just for one job, but for many jobs. And now we can do this thing that I was mentioning before of having a global view of data processing across jobs. Okay, so this dispatcher is aware of all the input pipelines. It can actually check which pipelines are alike and detect opportunities to cache and reduce actually the compute energy required to do this preprocessing. Okay, and to sort of gauge what benefits could we expect from caching in something like the Google Fleet, we looked at, how frequently is the same input pipeline re-executed. And so the way to read this CDF is we have, over this 1 month period where we analyzed millions of jobs, there were a certain number, which we again there's a few distinct input pipelines, which were ordered here from normalized number of input pipelines from most frequently executed to least frequently executed. And the blue line here is a CDF of input pipeline executions, right? So some input pipelines are executed much more frequently than others. And this here is the 1/10 or 10% of the input pipelines are accounting for something like 77% of input pipeline executions. So if you could detect which input pipelines are the heavy hitters, you can absorb a lot of the actual executions of input pipelines. And the orange line is showing a similar thing, but we've weighted each unique input pipeline by its compute intensity. And so these big jumps are input pipelines that are particularly compute intensive. And the way we actually detect what's a unique input pipeline is we're hashing the actual operators and the names of the input files that are fed into the input pipeline. So that's kind of how we pretty naively detect whether a pipeline is distinct or similar to, or the same as another one. Okay, so and why is it that we can have so much opportunity for caching here? It's because of common ML workflows like hyperparameter tuning, where you're changing things about the model, but actually your input pipeline is the same. You're reading the same input data, you're preprocessing in the same way, and you're doing this for many jobs in parallel. And so this motivated then adding to the service a cache, which can be used to cache either source data, if it's just clear that you need to read this data often, but you might preprocess it in different ways, or it can also be used to cache preprocessed data or partially preprocessed data. So the idea would be to detect portions of input pipelines that are frequently reused, and then if it's worth it, cache the, if it's a throughput optimal thing to do or a cost optimal thing to do, cache that instead of re-executing all the time. And again, those decisions of what to cache is something that we want to optimize for the user. Okay, so this is the Cachew system that we built, and it's open source. It's built on top of this tf.data framework in Tensorflow, and it is something that you can use with other ML training frameworks as well.
There's a question.
Yes.
In the previous slide, just out of curiosity, I was just wondering what are the types of the operators that makes this jump in the computation time, like which operator?
Yeah, good question. Yeah, unfortunately, in this, so you're asking like, what is super compute intensive about these pipelines? And is it really the operator, or it could also be kind of the volume of data that they happen to have executed with, actually. So at this level of the analysis, this kind of, you can get this fleet-wide perspective, but it's quite hard to actually drill down and see. You have to, see what's the username for this job, contact them, what are you running, and things like this. So we did that a little bit to some extent for some, clear outliers, but I don't have all the insights as to, what is happening here. Yeah, I would also be curious to know. Yeah, cool. Okay, and I'll highlight Dan Grau as the PhD student who has been leading the Cachew project. Okay, so the main kind of things we're addressing here is this auto scaling and then the caching. Maybe I'll just kind of give some intuition for why it's not always a good idea to cache, even if you might have space for it in your cache. First of all, caching the results of the input data pipeline will only help you from a performance perspective if input processing was the bottleneck, right? So you first have to check that, you're input bound, that it's worth considering caching. And then you also have to wonder, well, the transformed data, if you're doing all kinds of random permutations and inflating the size of your data, you have to worry about how large is the transformed data set that you would cache, because at some point reading that from storage might saturate your cache IO bandwidth and might not be that much faster than computing things on the fly. And the other thing to worry about with caching is that if you just reusing things across jobs is typically fine, but reusing within a job, there is opportunity. You might be visiting the same data, for multiple epochs. But if you just naively read results from a previous epoch of the job, then if the point of your pipeline was to introduce some randomness and so on, of course, just reading from cache would remove that randomness, and that can hurt your ML accuracy. So we sort of, at the moment, sidestep this by asking the user to give us hints as to where in the input pipeline it is safe to cache from an ML accuracy point of view. And then from candidate locations, we will pick what's the throughput optimal place to cache. And in some cases, it might be to not cache at all. Okay. So yeah, jumping to sort of how does this caching policy work? Here's, for example, a bunch of user-defined functions that the pipeline consists of, and we would ask a user to tell us, where is it okay to cache from an ML perspective? So let's say before you start introducing any randomness, and then the Cachew system will pick what is the throughput optimal place out of these candidate locations. And so these auto cache ops are just hints, and they will either be, at most one location will be converted to a cache, or in some cases, they're all treated as no ops if the best thing for throughput to do is to not cache at all, but just compute on the fly. And so the way this works is relying on the fact that ML training is quite predictable, repetitive. You can profile things in the beginning, and you can say, if I just compute, how long does it take me to do it? And you can say, okay, what's the output size of this whatever is produced at this location of the input pipeline where I have my candidate auto cache op, and I can have a model of, what's my storage bandwidth? If I'm reading a certain, volume of data from there, how long is that going to take? And then I just need to compare. Is it going to be faster to read from storage, or is it going to be faster to actually just compute on the fly? And I can do this for every auto cache op location and pick the place that's going to result in the highest throughput. So that's the intuition for how the auto caching policy works. We're basically analyzing metrics that we can collect in the tf.data runtime while the job is running. And then we can rewrite the pipeline to insert a caching op if we deem that it's worth doing. Okay, and then the other aspect of Cachew is not just do you cache and what do you cache or not, at which point in the pipeline, etc., but also, how many workers are you using to do this preprocessing? And you probably want to retune this after you decide whether you're caching or not, right? Because if you're reading from cache, the amount of workers you may need might also be less. So what's the intuition for the auto scaling? I think I mentioned this a bit earlier as well. The idea is you want to make sure you eliminate the input bottleneck. And so use as many remote resources as you need to do that, but not more. So any additional ones past that point where you've removed the input bottleneck are just extra cost and don't help you additionally save on training time. Now, how can you actually see when you've hit that sweet spot? Again, we can leverage the fact that, okay, each training epoch is composed of multiple batches, and we can monitor the batch time. It's a pretty good proxy of what the overall training time for the job will be. In terms of if we optimize batch time, then we're optimizing also the overall training time. And so the batch time, we can think of it as being composed of time to get the actual input data and time to train on that input data batch. And what we're trying to do is get this green part to go down to 0. We want to eliminate that input bottleneck. And it turned out to be quite error prone, or just quite noisy to really try to measure this separately from the model training. And instead, a more reliable way was to just sort of keep going gradually down, adding workers as you go. And at some point, we realize that adding more workers doesn't help. Your batch time plateaus. And that's because you've reached the model bound phase. And then you know that you can stabilize at a certain number of workers, in this example 4. So nothing fancy really in the policy, but it helps actually find the sweet spot. Okay, any questions about that? I guess maybe just quickly seeing this in action, and then I'll conclude and leave a bit of time for some questions. So the idea is over time, Cachew would be scaling up. So what we have on the y-axis here is the number of workers. So we'd be scaling up the number of workers until we converge. And during that time, we would be also evaluating, what's the compute time versus what's the expected time if we are reading from cache. And we can make a decision of whether caching is the right thing to do. And let's say it is. So then we need to do another iteration where we are actually now storing the results that we want to cache. Okay. Here we actually end up scaling from scratch. An optimization here would be to keep 3 workers, but anyway. And then now in this next phase, we can actually just read from cache, and we can now retune how many workers we actually need. The red job is the one we care about right now. And then what's also nice is, okay, so we converged to 2 workers now. We're reading from cache. This is now less compute intensive. We need less nodes to do this. And what's also nice is if a second job like this blue one comes around and it needs to, it's reading from the same input files and preprocessing them in the same ways, this will be a cache hit. And it doesn't have to go through this profiling stage, it can just directly start reading from the cache. Okay, it doesn't necessarily mean it's going to converge to the same number of workers, because maybe this is a different model downstream, or maybe it's using much, higher throughput GPUs or TPUs or whatever. So in this example, we made the downstream model fetch data 2x faster, and it needed 2x more workers to do this. All right. So that's kind of Cachew. I'm going to skip the other performance results and maybe just conclude with a little bit of a teaser by what I mean by data efficiency, which is kind of this next topic that we're starting to think about, but still very early on, and I think could be really interesting for collaborations also, if there's other folks interested from your side. Okay, so this kind of one thing, working on data processing at Google versus working on it in academia, kind of got me thinking, what are all the differences between these kind of research data sets that we use and the data preprocessing we do on them that we can do easily in the open source world versus, what happens with real data sets. And when you deploy ML in practice, one of the things that's not captured by these academic data sets is that real data is often dynamic. So you might have data you're collecting over time, so your data set just grows. Or you might have shifts in your data. This is an example of a yearbook data set where the appearance of people is also changing over time with different fashion, et cetera. And there's also data needs to be deleted because of privacy reasons or other regulations. And so the other thing that comes up, and that I think not a lot of system infrastructure yet to really handle, is how do you adapt your models as your data is dynamically changing, right? And there's evidence, this is some example from Grubhub, which is a food delivery service, saying if their baseline is to not retrain the model at all, that's how much, let's say that's the baseline for this click-through rate metric that they have, then weekly retraining helps increase that by about 2.5%, but daily retraining would help increase that by almost like over 20%. So these are pretty significant deltas in interactions that they have with customers. But of course, retraining models is not free, right? The cost of training, going back to that theme of cost, is proportional to how often you train and how much data you visit. And so I think these are both really interesting questions, one to retrigger training, what data to train on. And it seems like from talking to people in industry, it seems like these decisions are still done in a very ad hoc way. And so kind of an emerging research area that we've been working on is first building an open source platform where users can plug in different training triggering policies, different data selection policies, and the system would handle the challenges of managing the data sets and the metadata associated with the importance of separate elements under the hood at scale. And so this is work in progress. We have already open sourced the system. We have a short kind of workshop paper, and this is work by Maxi and Fotini in my group. All right, so I will conclude by saying, we talked about ML having a cost problem. We said input pipeline bottlenecks are a common thing we need to watch out for and be careful how we design the system. And this is what motivated Cachew to kind of auto scale and distribute data processing, manage caching, and the kind of most recently what we've been thinking about is adding this extra dimension of what happens when data is dynamic and what is the infrastructure you need to explore those kind of questions. So thanks a lot for your time and happy to take more questions.
Thank you. Questions here? So yeah, thanks for the amazing talk. So that's really very interesting besides. When I'm saying this, I see like everyone nodding here. So one question about like the scope within which those results apply. So I mean, you have shown results from the computer vision domain. From what I was seeing, and I was wondering, you also mentioned GPT-3, so I'm wondering about like how complex preprocessing needs to be in order to make this maximally beneficial. I mean, for language models, for causal language models, it's relatively simple preprocessing. Does that also lead to significant?
That's a great question. Great question. So yeah, a lot of the kind of the places where input data processing tends to become quite easily a bottleneck is more in these sort of vision type of workloads. I mean, it also depends the way that the ML, hardware platforms are built today is they actually have a lot of, like a TPU machine on Google Cloud will have 96 core CPU cores with it. So there's already a lot there. And therefore, if you run some sort of language model, it's usually you're not going to have a very prominent input bottleneck there. However, what's interesting is even if you don't have, even if you're not bottlenecked on the data preprocessing, this disaggregation, this was kind of something along the way we realized disaggregating input data processing can still have benefits in something like language models, because you are training, these models are usually quite large, you train them in a distributed fashion. And what's interesting about the inputs to language models is that it's often kind of sentences or sequences that are different lengths. And in training, if it's something like data parallel training, each training node is getting a batch of data. And if this batch is different sizes, if some training node is getting a bunch of longer sequences and another is getting a bunch of smaller sequences, then you can have stragglers, basically. And that leads to then communication stalls and other things that would slow down your pipeline. And what's nice about disaggregation is you can actually coordinate which samples you're sending where, and make the batches sort of more uniform to avoid stragglers. So this is kind of orthogonal to the other benefits I mentioned, but this happens to be the benefit that currently we find is most useful for these sort of language model type of use cases.
That's super interesting. Okay, that makes a lot of sense. Okay, very interesting.
I have a question. So can you talk a little bit about your intuition in modern about when to trigger training? Like, are you using some heuristics or?
We're starting with heuristics. Yeah, we're starting with heuristics and kind of chatting with companies to see what are people doing today. I mean, a very kind of basic thing you can do is sort of on regular time intervals, like daily, weekly, etc. One of the things, I mean, our first step is literally, first of all, getting open source data sets that have this notion of some sort of time and dynamic nature incorporated in them. So I sort of skipped over that slide a bit, but some of the things we're thinking about, let me just go back. So there's this Criteo data set for recommendation systems, or a push shift Reddit to something where you can get Reddit data with timestamps. There's some autonomous driving data sets where maybe things aren't evolving over time necessarily, but you have just more and more data that you're incorporating. And so these are, our first step is really building the benchmark suite and the open source platform. And we're starting by heuristics and also looking at ML literature and what kind of policies people have been using. Oftentimes it's on smaller data sets and things like that. So we want to take ideas that have been proposed and start by exploring those in the context of larger and hopefully more representative use cases. And then we're hoping that'll give us some ideas to come up with new policies and so on, but we're not at that stage yet. Yeah.
Sure. One follow-up. Are you also thinking of modifying the data processing pipeline, like for the new data set? So rather than just retraining, you may have to modify the data processing pipeline also.
It's a good question. And what do you do about data you've pre-processed before? I guess it's a good point. I think that's not what we've thought to do first, but I think it's definitely, or in general, this comes up. Maybe you realize that you have drift because some sensor was discolored or something, and now if you account for that in your pre-processing, it solves all these things, and your model becomes much more accurate in general. But then maybe you also want to apply that pre-processing for older data you saw and retrain everything. So I definitely think the pre-processing part of the pipeline should be on the table of things you might optimize. But maybe not just for the new data, but just in general. Yeah, I think it's there's a lot of interesting questions, so it's a good point.
Thank you.
Yeah.
Right. A little bit above the time. But if there's like any more questions, if that is okay for you, maybe people could send
Feel free to reach out. Yes, absolutely. Yeah.
Awesome.
Thank you.
All right. Thanks so much for the visit. That was great.
Thank you.
Thanks so much for coming by. All right. Let's.
Thanks for having me. Yes. I hope to meet you all in person soon. Okay.
Yes, same here. All right.